All right, today's lesson is 68. It's the probability multiplication rule. What's our objective, class? Get ready?
Probability multiplication rule.
Probability multiplication rule. Today we're going to learn about if I took two events, rolling one dice and rolling another dice, how many total possibilities there are. That's one topic we're going to talk about. We're also going to talk about if I roll one dice and roll another dice, what's the probability of rolling maybe an even number on each dice. So we're going to talk about those two things, how many possibilities of two events and what the probabilities are. It's pretty cool. You're going to like how it comes out. So, if I was going to do a tree diagram to do two events, I'd have to do all these possibilities, like heads, tails, heads, tails, heads, tails. Same thing. If I had two dice, if I were rolling both, I'd have to do, roll 1 is 1, 2, 3, 4, 5, 6. Roll 2 is 1, 2, 3, 4, 5, 6. I'd have a lot of possibilities. In fact, I'd have this many possibilities. If there are 6 possibilities on one dice and 6 possibilities on another dice, right off the bat we can say there's 6 times 6, there's 36 possibilities, and that is our shortcut for the fundamental counting principle. What is it called? Get ready?
Fundamental counting principle.
The fundamental counting principle says that if I've got one event that has 6 outcomes, or M, and a second event that has, for example, 6 outcomes, my total number of possible outcomes are 6 times 6, or 36 in this case with the dice. So we're going to multiply each event's number of outcomes to find the total number of outcomes. All right? So that's called the fundamental counting principle. What operation do we use, think?
Fundamental.
What operation?
Get
ready?
Fundamental counting principle.
Oh, sorry, I'm looking for the operation. It's multiply. So we multiply our outcomes. What do we do? Get ready?
Multiply our outcomes.
Multiply our outcomes, but at least you guys know the name of it now. That's really good. Okay, so let's take a look at this cool case, all right? So we had 36 possibilities. My question now, what about probability? We know there's 36 outcomes. What about probability? Jacob?
You said that we do like the even numbers. How would you necessarily do that?
We're going to do that, okay? Okay, the old-fashioned way, we would have done this huge table. Again, so this is dice 1, this is dice 2. My first dice, I rolled a 1. Maybe my second dice, I get a 1. Or I might get a 1 and a 2, or a 1 and a 3. Do we understand how to read this? Okay. So if I were to ask the question, what is the probability of rolling 2 even numbers? I would go, okay, well, here's an even and an even. Even, 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 even. Those are odds. Even, 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 even. Okay, 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 even out of a total of 36 possible outcomes. That reduces to 1/4. So I would say the probability of rolling an even and an even is 1/4. I want to post to you a brand new shortcut that you're going to love. It's called the multiplication rule for probability. What is it called? Get ready?
Multiplication rule of probability.
The multiplication rule for probability says I can take the probability of each event and multiply them. So the probability of rolling an even on one dice, that's one event. Well, my even numbers are 2, 4, and 6. Okay, so my probability of rolling an even on one dice, there's 3 even numbers out of a total of 6 numbers on the cube. It'd be the same for the second dice, right? The probability of rolling even on the second dice, or my second dice, all right, is 2, 4, or 6. So there's 3 desired outcomes out of a total of 6. Well, these reduce to 1/2 times 1/2. 1/2 times 1/2. Remember, I multiply across the top. 2 times 2 is 4. My probability is 1/4. That's what I got by counting up my huge table. And all I had to do was two probabilities and multiply them. That's called the multiplication rule for probability. What is it called? Get ready.
Multiplication rule of probability.
Multiplication rule for probability. It says if the events are independent, you can take the probability of the first event and multiply it by the probability of the second event. And I saw a jaw drop. Going, yes! It makes it so much easier. Let's talk really quick on independent events to make sure you guys understand. Let's say I took a spinner and a dice, and I said, what's the probability of, if I had two events, of getting a green and a 5? Okay. Well, I could say, well, once I roll the green, it doesn't affect the dice at all, right? If I roll the dice, it doesn't affect the outcome on the spinner. So these are independent events. They don't affect the outcome of the other. So I could say, well, the probability of green is 1/4. The probability of a 5 is 1/6. I would multiply them together. That easy. 1/4 times 1/6. 1 out of 24. Okay, Jacob?
Would it necessarily be that? Wouldn't it be, you add, pretty much like add the denominators, so you have the 2 out of 10 and the 1/5?
When you're with the multiplying rule, I already erased it. You always multiply the denominators and you multiply the numerators, and then you can simplify it. Okay, good question. AJ?
Your chips are falling out.
Oh, there's a slit in the bag. Okay, did I lose all 3 blue ones? Okay.
Yeah.
We're going to pretend, we're going to need them for our next one. We're going to talk about red marbles and blue marbles and make sure you guys understand the multiplication or the independent events. So let's say I've got 3 new blue chips because I only see one on the card. I don't know where the other ones went. They're somewhere. I'll get them in a minute. So let's say I've got 3 blue and 2 red, and pretend they're marbles and pretend my hand is a bag. If I reach in and say, what are the chances of getting a red, right? Let's see what I pull out. I got a blue. But let's say I take the blue and I take it and keep it out of the bag. So now I say, well, what are the chances of getting a red now? It changed, right? Because I took 1 out. Now I have 1 fewer marbles. So when I calculate my probability, it's going to change. We have a different lesson on this topic. So if I replace the marble, it resets the probability, and it's the same probability, right? The same chances. So whether or not I pull a red or a blue, as long as I put it back in, the chances are still the same every time I pull a marble out. Okay, so that's what we mean when we say independent events. So let's figure out, in this case, with 2 red marbles and 3 blue, the probability of drawing a red and a blue, there's 2 events here, would be the probability of the red times the probability of blue. What's my probability of getting red? Well, how many reds are there? 2. How many total dice are there, think? Or total marbles? You ready?
5.
Oh, I didn't get everybody, but that was right. What class?
5.
5, good. The probability of getting blue, how many blues are there, think? Give it, John. How many blues? 3. No. Yes. 3. Okay. How many total dice, class? Get ready? 5. I need marbles. Okay, so the multiplication rule says you can multiply each event and get the total probability. So 2 times 3 is 6. 5 times 5 is 25. And then it won't reduce because nothing cross-canceled, so nothing will reduce here, and that's my total probability. We got one more. Let's say I've got a big stack of cards, and they're just letter cards. They're not face cards. They're just letters. They have 26 uppercase letters, so capital A, capital B, etc. And then 26 more cards that are lowercase, A, B, C, and so a total of, how many cards total do I have? Kate?
52.
52. We got to know that. We're going to shuffle the stack and select one card. What is the probability of getting an uppercase that is also a vowel? So it's kind of like I've got 2 criteria, so it's almost like 2 events. Okay, so I want to find out, well, what's my probability of getting an uppercase? And what's my probability of getting a vowel? All right, some of you already know the answer. Okay, help me out though. My probability of uppercase, I need to know how many uppercases are there? Jacob?
1 out of 2.
Okay, but there were 26 uppercases out of, we said 52 cards. that's this one. And then the probability of a vowel, how many vowels are there? I've got my 26 upper cases, 26 lower cases. Jacob?
Well, I'm not Jacob.
Sorry, Lucas, I owe you another ticket.
And also, it depends because some people think 5 vowels, but Y can also be a vowel.
Let's say Y is not a vowel in this one. So if there's 5 uppercase, A, E, I, O, U, and then there's going to be 5 lowercase, A, E, I, O, U. 10 total. Out of a total of still 52 cards. So the probability rule says to multiply them. So I don't want to multiply big numbers. Let's make them smaller. Let's cross cancel. 26 and 52, they're multiples of each other, once and twice. 10 and 52, they're both even, so I could cut this one in half, make it 5. I could cut this one in half and make it 26. And then I'm going to go 1 times 5 is 5. 26 times 2 is 52. And it won't reduce any more because there wasn't anything else that would cross cancel. So my probability out of 52 cards, in 52 trials, 5 of them I should be pulling an uppercase that is a vowel. Jacob.
Couldn't you just do this in an easier way and just say that you have 5 out of all the 26 and just put that over your 52?
I have 5 out of my 26.
You have 5 of your uppercase vowels out of your 26
True.
uppercase vowels. So couldn't you just put that over 52?
You still would have to say, you'd still have to take into account your other 26 cards. I see what you're saying though, yeah. This just shows the math logic behind this formula, okay? Any questions on the probability, the multiplication rule, and the fundamental counting principle? All right, they're both kind of the same idea. Each event multiplied by each other. Okay, you've got a 20-second stand-up break. We're on page 460.